Yesterday, we graphed the parent function. So you guys have basic shape of what these functions look like, but today our goal is to graph by transformations. So yes, you're graphing a quadratic, and yes, you technically already know how to graph some quadratics, but specifically when it's in this form. Okay, what was the name of this form? Standard form, intercept form, vertex form, vertex form. Okay. Specifically when it's in vertex form, you have a lot of information which enables us, instead of graphing by plugging in random points, but to graph by using the transformations. Okay? So we're going to look at that two ways. There's part of my screen that you can't see, but right above this on your paper, you guys have this written. So first we want to understand what transformations are happening to our function. So this kind of reviews the homework that you guys had done before. Okay? So A, H, and K. What is my A value here? 2. And my H value? 5. And my K value? -4. Each of those values is causing a transformation. What kind of transformation is this 2 going to cause? Rasmus? Good. Okay, so there's a vertical stretch. And then I'm going to write times 2 here for what we're going to do today, because we're actually going to do the stretch. And I want to understand how much I have to stretch by. Okay? What is the H going to cause? What kind of transformation? Jonathan? Good. Okay, so translate 5 units right. All right, and what about my K of -4? What transformation is that going to cause? Josh? Good. Another translation, 4 units down. So if you guys could just take the parent function that we drew yesterday, and you could move it 5 units to the right, 4 units down, and stretch it by a factor of 2, you'd have your new graph. So that's what we're going to do, and we're going to do it graphically and with points so that you can understand how it's working each way. So graphically, I'm going to graph on here the parent function. Okay? I'm going to graph it in a different color than I want my final one. I'm actually going to graph it in like orange or something that's a little bit lighter than that, so that I know that's not my final output. So I have to know the parent function really well. Okay? And what I know for the parent function are these points. So if you're wondering where I got these points and you think it's like math teacher wisdom that got these points, like kind of, I do this all the time, but you know these points too because you need to have your parent functions memorized. Does that make sense to everybody? So you can't keep looking and going, oh, she just knows that because, no. I know it because I've spent the time memorizing it, and for this course, that's going to help you be successful in the graphing that you have to do. So that's the parent function. Numerically, the parent function is this simpler equation, and those points that I just graphed came from this chart, where this right here was our vertex. So far, so good with everybody? So all we've done is put the parent function on here. So notice I'm not going to just start plugging random things into here. Here's the problem with plugging random things into here. Plugging something in for x and getting a y that goes with it will for sure be a point on this parabola. But you'd have to be smart about what you choose if you want to see the vertex. You could plug in -2, -1, 0, 1, and 2, and you would not even get the vertex of this parabola. You would just have one part of it, okay? Because of the different shifting and transformations that have been made. Okay? So graphically, let's do everything that this says, and then we're going to do the same thing numerically and make sure that our points line up with that. So graphically, if this graph has been vertically stretched by a factor of 2, that means the y coordinate distance from the vertex, because it started at 0, and 0 times 2 is still 0, so that one's not going to change. But these other points are vertically going to stretch by 2. So they're not going to do anything horizontally, nothing left or right. But however far they used to be from that x-axis or from that vertex point is now going to get multiplied by 2. So this point right here, how far is it from the vertex point vertically? I'm only thinking up and down right now. Jonathan? Right now, it's only 1 unit. Okay? But I'm going to take that distance of 1 and I'm going to stretch it, meaning I'm going to say they used to be, think about your greatest integer steps, right? When you put a 2 in front of there, they used to be 1 unit apart, then all of a sudden they were 2 units apart. So this used to be 1 unit away from the vertex, but 1 times 2 is 2. So that point is now going to be 2 units above the vertex instead of 1. Since this point on the other side has the same vertical distance, it'll look the same after being vertically stretched. Now, this other point out here at 2, 4, again, not doing anything to it horizontally, just doing a vertical stretch. How far is it from the vertex vertically? Currently, 4. That distance needs to get stretched by a factor of 2. So it was a distance of 4, but now 4 is going to get times by 2, and the new distance will be 8. Notice I'm measuring everything from my vertex point because that started on the x-axis or at that 0, okay? So the points that I have right now, I shouldn't have made them such a dark color. This is not the final product because I've only done one transformation, okay? I have done a vertical stretch by a factor of 2, okay? Now, I also need to translate 5 units to the right and 4 units down. Are you guys okay if I do those at the same time? Meaning, I'm just not going to replot each one. So I'm going to take every point that's now blue on my graph, and I'm going to move every point 5 to the right, and then 4 units down. Okay? So this vertex point, 5 to the right, and 4 units down. The point that was 1 to the right of it isn't 2 above it. The point that was 1 to the left of it is 2 above it. Or you can literally count 5 over and 4 down, and you'll get all this stuff. I like working around the vertex and knowing the distances because it helps me do things faster later on when I'm used to it. So the point that's 2 away from the vertex horizontally is now 8 above it. Or you could count, and you could go 5 over and 4 down, and you'll see that same result. Okay? So this graph in black is my final graph after my transformations. Okay? So you guys are going to get good enough soon after practicing with this a bit that you're going to be like, I know the vertex is at 5, -4. Okay? Normally from the vertex, the points are 1 away and 1 above, 2 away and 4 above. Oh, I'm going to stretch those out by 2 from there. And you're going to do a lot less work than we did right here, and you'll be able to do it. You don't have to be there right now, but we're going to be doing enough of this that you'll get there eventually. Okay? All right, now, how we could have done this numerically with the points. Okay? We could actually take this chart and just adjust the x and y values based on the transformation. This vertical stretch of 2, a vertical or horizontal transformation? Vertical, meaning it's affecting x values or y values of the points? Y values, the vertical stuff on the graph, right? Remember when we were doing it on here? We didn't care anything about the x. We didn't touch it or move it. We only times the vertical distance. So the y values of the graph are getting stretched by 2 or multiplied by 2. What else is happening vertically to the graph? There's 2 translations. Which one's a vertical one? The down one. So the y values were affected by being multiplied by 2 and then subtracting 4, so to speak. Okay? So I can literally take all the y values that used to exist in my chart. I can times them by 2 and subtract 4, and I should get the right y coordinates that go with the adjusted x coordinates. What is the only transformation here that adjusted the x coordinates? 5 right is the only horizontal thing that we did, right? If you want to move something 5 right on the x-axis, what do you do to the x coordinate? Add 5. Okay. So watch if we take everything from our chart over here and do these transformations to it, we should get these points that we got right here. So I'm kind of giving you guys 2 ways to do it. If you really like numbers, there's a numerical way to look at it. If you really like the picture and the graph, there's another way to look at it there. So -2. plus 5 would give us 3. Negative 1 plus 5, 4. 0 plus 5, 1 plus 5, 6, and 2 plus 5 would be 7. I'm not going to go plug these in. Now I'm just going to go affect the y values. Why am I not plugging them in? This chart already squared stuff, right? And I'm just saying, oops, this should happen before it's squared, and this should happen after. Let's see what happens. So this output used to be 4. Now I'm going to take it, times it by 2, and subtract 4. So 4 times 2 is 8, minus 4 would be 4. The next output was 1. 2 times 1 is 2, minus 4 is negative 2. The next output was 0. 2 times 0 is 0, minus 4 is negative 4. The next output was 1. Okay, 2 times 1 is 2, minus 4 is negative 2. And lastly, we had 4. 2 times 4 is 8, minus 4 is 4. Are these the points we plotted on our graph? Oh, check. 3, 4. 4, negative 2. 5, negative 4. 6, negative 2. 7, 4. So I could do it this way, right? If I understand the transformations, I can numerically figure out the points from the parent function points. Or I can graphically and visually perform them on the graph and take the parent function and do those same things and get these points. You're doing the same thing, but one time we did it graphically and visually, and the other time we did it numerically. Okay, both times starting with the parent function. Is this all right with everybody? So this allows us to graph using transformations. These transformations will be used throughout the entire course this year. So if you can learn how to do it well, right here with quadratics, then when we get to cubics, yeah, new parent function and new shape, but all the same things happening to them as you go. So you'll get really good at those graphs. Okay? All right. Vertex. Our vertex comes from our h and our k. So from the equation, you already pulled out h and k, and we already knew our vertex was supposed to be at 5, negative 4. Did that work out correctly in our graph? Did it work out in our chart? Yeah, our vertex point now ended up at 5, negative 4. The x-intercepts for our graph, okay? In order for us to get the x-intercepts of this, we have to actually solve the quadratic equation, which is kind of what the remainder of this unit is about. So for right now, we're going to leave the x-intercept part blank, but next week we'll be filling that part in, okay? How do I find the y-intercept? So there's a standard way, no matter what kind of equation you have, how you find the x-intercept and how you find the y-intercept. If something is a y-intercept, what do you know about it? The x has to be equal to 0. So that is literally what you need to do to find the y-intercept. You need to take our equation, and you need to set x equal to 0. Okay? So 0 minus 5 is negative 5, and if I square that, I have 25. 2 times 25 is 50. 50 minus 4 is 46. And you might think, no way, but look at our graph, okay? Still got 3 spaces till it's going to hit this y-axis over here, and it's starting to climb quite quickly, right? It's possible it won't hit till 46. That visually makes sense with what I have here. What's the domain? Marcus? Good. So the domain is all real numbers, or negative infinity to infinity. What's our range? Brandon? Good. Y has to be greater than or equal to negative 4. And in interval notation, we would say from negative 4 to infinity. All right. What is the increasing interval of this graph? Natalis? Okay, good. So yes and no. You're identifying the right part. So it is increasing from negative 4 to infinity if we're talking about y values. But remember, the increasing interval is saying for these x's in the domain, my graph is displaying increasing behavior. So she's right about identifying this part, but this part corresponds to what x values in the domain? Brandon? Good. So from 5 to infinity. Is everybody okay with why we're picking 5? So again, make a little note next to the increasing and decreasing interval if you have to, that we use domain values for this, that we list the x's where the graph is displaying that behavior. So our increasing interval is from 5 to infinity. And what's our decreasing interval? So we're saying from the x's from here over is our increasing interval. And so this would be decreasing, right? So how are we describing that? Negative infinity to 5. Good. Is the graph 1 to 1? No. It is a function. It passes the vertical line test. Every x only corresponds to one y. However, there are y values, okay, like right here, that would correspond to 2 different x values, so not 1 to 1. We're leaving the rate of change blank right now, like we talked about yesterday. What is the axis of symmetry here? Jonathan? Good. X is equal to 5, so that vertical line going through the x coordinate of the vertex. What is the minimum value of the graph? -4. And what is the maximum value? None. And then I cut off on mine so that these could stay a little bit bigger. You can just cross off the asymptote part like we talked about yesterday, or write none until we get to something that actually has asymptotes. So your homework tonight will mostly include problems like this, where most of the transformations are happening vertically, because like I talked to you guys about yesterday, the regular Algebra 2 courses really only study horizontally shifting and reflecting, but we study all of them. So if you turn it over on the back, we have a little bit of a more complicated problem to solve. Sorry, there should be a negative right here. Okay, so in order for us to see this written in the correct form, first of all, we need to separate that 1/3. It's not going to come all the way out of the quadratic, but we need to see it separately than our x minus h, because the formula doesn't say b times x and then after that minus h. X minus h is one group every time in our formula, which means if there's a number multiplying x, it was also distributed to your h, and you need to undistribute it or distribute it out to see what was actually there before. Okay, so I know that I want this to be 1/3 because I know 1/3 times x would make that 1/3 x. And then I'm going to be able to see my h value properly based on what's left right here. Now that x with a coefficient of 1 is grouped with h, not with a different coefficient. Okay, what number should be here? +3. Good. So those of you that struggle with this, 2 ways to do this. 1/3 times what will make 1? That's essentially the question you're asking yourself. Or literally do what you do when you distribute something out. Take what was there and divide it by the number that you took out. So 1 divided by 1/3 would give us 3 that's left. Okay? All right. So then let's make a list of our transformations. Now that we know we could use that chart in addition to using the graph, we'll kind of separate like the vertical and the horizontal ones. Okay? So let's make a list of vertical transformations. So vertically, what is a transformation that's going to affect our graph? Actually, I'm going to list the vertical ones. It's fine. Okay. Yeah, Brandon. Okay, so the 1/3 is actually going to be horizontal because it's going to happen in here with the squared. So, good. So the -2 is actually 2 vertical transformations. What 2 transformations is it? Jonathan? Across the x-axis, okay, and a vertical stretch by 2. So we have a vertical reflection and a stretch specifically by 2. Caden? Question? Oh, no. Okay. Okay, so what's our other vertical change that's going to happen here? Natalie? Good. So we're going to have a vertical translation up 5. Is that okay with everybody? So what that means for our table so again, this is for the parent function. What's going to happen to the y values if these are all of our vertical transformations? The new y values will be the old y values with these things happening to them. So arithmetically, with arithmetic, how do those things look numerically? Marcus?
-2y.
So -2 is going to multiply y. And what else? Jonathan? +5. And it kind of looks like if you just covered this up, exactly what's happening. Because the vertical stuff is really straightforward, right? When it says +5, the transformation is literally +5, okay? It's the horizontal stuff that's a bit more complicated to deal with. So with the horizontal stuff, what are the horizontal transformations that are here? Brandon. Good. So what is the 1/3 actually going to do to our graph? It's going to be a horizontal what? Good, stretch. So again, think about our greatest integer functions. If there was a 1/3 inside the bracket with x, what would have really happened is our steps would have gone, and they actually would have been 3 units long, right? So they would have got stretched out by a factor of 3. Instead of 1, they became 3, 1 times 3. So this is going to be multiplied by 3. Okay. What is another horizontal transformation that is taking place? Natalie? Good. Okay, our h here is -3, or in other words, it's getting shifted to the left 3. So we have a horizontal translation left 3. Okay? So our x values are getting times by 3, and they're getting shifted to the left 3. Okay? Is this all right with everybody? So numerically, you could take these x's, do this to them, and have new x's. And then you could take the y's they used to match up with, do these adjustments to them, and you'll have the new y's that those x's match up with. Okay? Graphically, we can take our parent function. You guys are going to get really good at knowing this parent function. Can you see why you'll get really good at it? All revolves around it. Okay? We could take this parent function, and we could physically go through these transformations. Okay? So let's say I go to do these two. A vertical reflection and a stretch by 2. This vertex would remain unchanged because if I try to reflect it over the x-axis, it's on the x-axis, so it's not getting reflected. And if I try to times its vertical distance from the x-axis by 2, it's on the x-axis, so its distance is 0, and times 2 remains 0. So that point stays. This point used to be 1 unit above the x-axis. Where will it get plotted after the vertical reflection and stretch by 2? Jonathan? 2 units, but not above because of the reflection. Below because we're reflecting it, right? So the stretch is causing it to move here, but the reflection is causing that to happen down here. Is everybody okay with that idea? So same with the other point that had the same vertical distance. Now again, this point up here, okay, it was 4 above the vertex. Where will it be now in relationship to the vertex, Chris? Good. Okay. It'll be at 2, -8. In other words, it's going to be double the distance instead of 4, 8 units away from the vertex, but not above, below because of the vertical reflection. And same with the other point. So here's my graph with those 2 transformations done. I'm not done. That's just those 2 transformations. Let's talk about this horizontal stretch, and we can just shift everything at the end. And again, when you guys get good at this, you can shift everything at the beginning. But if you shift your vertex at the beginning, because you should already know, where should our vertex end up being based on our h and k values? -3, 5, right? So a lot of people like to just go there first. That's great. But now when you do your vertical reflection, are you going to move the point negative 3, 5? No. Negative 3, 5 is the vertex point. It is the final resting vertex point of this graph. It doesn't move from that spot. So if you go to the vertex first, you have to be aware that you've changed things now. And when you reflect and stretch, now you're reflecting and stretching around the vertex point, not the axis, because you moved it off of the axis before you did the other things. Does that make sense to everybody? Okay, so just be careful how we do that. All right, so what about this horizontal stretch? Any ideas what that's going to look like? Jonathan?
Instead of being negative 1, positive 1, negative 2, it would be positive 3.
Perfect. Do you guys see how he only adjusted the horizontal distance of the point? So we already adjusted the vertical distance of this point, but now he's looking horizontally and saying, okay, you know what? That used to be 1 unit away from the y-axis or away from the vertex. But I'm going to take that 1 and I'm going to times it by 3. So now that point, instead of being 1 unit away from the vertex, is going to be 1 times 3, which is 3 units away from the vertex. And I already did the vertical, so I'm not going to adjust the vertical any. I'm going to keep it at the same vertical distance that it was. This point on the left side would be the same because it is 1 unit horizontally away. It will now be 3 units horizontally away, just in the other direction. So what about this point down here? This point that's at 2, negative 8. What adjustment is it going to have with this horizontal stretch? Where should it end up? 6, negative 8. Yeah, instead of 2 units away from the y-axis or the vertex, it's 2 times 3, which is 6 units away from the y-axis or the vertex. And again, we're not changing any of the vertical right now because we already did that change separately. So here's what our graph would look like. Sorry. Did a poor job. Okay. After our horizontal stretch. And notice everything we're saying, the graph looks like someone did that to it when we were done, right? When we did the first one, it was vertically reflected and it got skinnier because we vertically stretched it. Now we horizontally stretched it, so it looks like it got a little wider. And so all we have left to do now are our translations, okay? So let's take these groups of points, but now let's translate them. We're going to go to the left 3 and up 5. So this vertex point that was at 0, 0 is now going to be at to the left 3 and up 5. So at negative 3, 5. And you can either count for all your points, or you can just, now that you know this is the vertex, you can replot around your vertex all the points at the right distances. So there should be another point 3 horizontally away and 2 below from the vertex on each side. And then there should be another point 6 horizontally away and 8 below from the vertex. Sorry. So that would be our final graph. Okay? And again, if we did it numerically, we would have just adjusted all the points like you see here. So we would have taken the x-coordinate of negative 2. We would have done 3 times negative 2 is negative 6. Minus 3 is negative 9. 3 times negative 1 is negative 3. Minus 3 is negative 6. 0. So I would do this change for each of these. And then I would do the y value changes to the original y values. So 4 would get plugged in here. Negative 2 times 4 is negative 8. Plus 5 is negative 3. And then I would continue that for each value. I can see my vertex point there. These points should match what I have over there. Then I feel pretty confident when I'm done. You don't have to do it both ways, but some people like this better and some people like this better, so I'm kind of giving you both. Yeah, right? Are you sure? All right, so vertex is going to be at negative 3, 5. We've seen it show up on our graph and in our chart and according to our transformation. X-intercepts, we're going to come back and fill in at a different time. Y-intercept we would get by plugging 0 into our function. So think about plugging 0 for x in our original function. Gets rid of that fraction, so that's really nice. So we just have 1 here being squared, which is just 1. Negative 2 times 1 is negative 2, plus 5 is 3. So our y-intercept is at 0, 3, and hopefully you see that on our graph. That one even showed up in our table. Domain is still all real numbers. For the quadratics, it should stay that way. What is the range for this specific function? Brandon? Good. Or from negative infinity to 5. All right, intervals of increasing and decreasing here. What is the increasing interval for this function? Thinks they can give this to us. Remember, you're saying for these x values, the function is behaving like it's increasing. Megan? Good. From negative infinity till negative 3. So as you look at the graph from negative infinity until you get to negative 3 on the x-axis, you see an increasing graph. Okay? And so then when we look from negative 3, the rest of the x-axis towards infinity, the graph is decreasing. Is it 1-to-1? No. We're leaving rate of change blank. What is our axis of symmetry? X equals negative 3. Minimum value? None. Maximum value? 5. All right. So are we okay with